CCS research at the Program on Energy in Stanford University. The title for his talk will be International Coal Markets, Coal, Climate, and China. Richard is a former colleague of mine. We worked together for 3 years at Stanford. He is a very young guy, 27, 28, but when it comes to coal, he's a real dynamite. He is such an expert from market information of the second all the way to history of coal like 300 years ago. He is a real expert. So if you want to learn more about coal, not just in the US, but international market, it's just mind-boggling how this market works and how this market has become so much more complex and liquid over the last 20 years. Most of us are out of touch of what really coal means. So please join us for that talk. With that, let me introduce our speaker for this week, Armond Cohen. But before I do that, let me just tell you why I invited him. Not a real true story, but probably a funny one. A few weeks ago, we heard from a speaker at this symposium that Northeastern liberals usually tell us what to do when it comes to environment, right? We all remember that. So I thought, well, I don't know what was meant, so I decided to invite one and hear from him what really they have to tell us. So that's really the story why I invited him. So Armond is the co-founder and executive director of the Clean Air Task Force, which is a nonprofit organization dedicated to reducing atmospheric pollution and commercializing innovative clean energy technologies. He has just, like many of our other speakers, but really the breadth of involvement that Armond has had is just mind-boggling. So currently, he's a member of the US EPA Clean Air Act Advisory Committee, a member of the Keystone Energy Board, a member of the founding board of the Institute for Gas Drilling, and he has also served on the policy subgroup of the recent National Petroleum Council study. You can see gas, oil, clean air, just an extraordinary range of involvement when it comes to energy issues. He is the co-lead on 2 studies of U.S. energy innovation policy, both of them done in collaboration with the Center for Science Policy and Outcomes. One of those studies is Innovation Policy for Climate Change, and the other is 4 Policy Principles for Energy Innovation and Climate Change. Armond is an honors graduate from Harvard Law School and Brown University. The title for his talk is, I have a different one, but I'll read that one, Climate Realism, or Why Small is Not Always Beautiful on Others. And what he's going to tell us is how to solve the climate change problem, reflect how to solve the problem at scale. Please join me in welcoming Armond.
Thank you very much. Thank you. Can you hear me okay? Is that okay? So I'm going to do all that in a half an hour, and then we'll have a half hour of discussion after I've told you how to save the world. So although I'm a Northeastern liberal, and I'll confess to that, a lot of what you're going to hear today may be a little bit outside the box for what you might expect, because while a lot of the environmental movement tends to gravitate towards small solutions, so-called soft energy solutions, one of the thrusts of my talk is that small isn't always beautiful and it's not always going to do the job. And we have to actually seriously think about the fossil part of the equation, at least for the next several decades, as well as nuclear and other things that we might not ordinarily think about dealing with. So let me start with, let's see if I can get this thing to work. It's only going to go from here. So a few takeaways. The first point, which kind of sets the stage for everything else, is we have a big drop in carbon to do. You know, when we talk about national legislation, it's often, well, we'll get a 15%, 17% reduction in carbon dioxide. I want to make the case that we may need to drop to 0 or even negative carbon emissions, at least from the energy system, by 2050, which gives you a whole different way of thinking about the problem. Today's soft solutions, and by that I mean primarily renewable energy and energy efficiency, won't get us there physically or economically, and therefore advanced fossil with carbon storage and nuclear energy can't be ruled out and in fact should be pursued and developed. For all of that, for both the fossil, the nukes, as well as efficiency and renewables, we need much better, cheaper technology, and therefore we need a lot of innovation. We don't have all the things we need, which is what you often hear in the political rhetoric. Fortunately, globalization may work in our favor. in terms of that innovation process, and I'll give China as an example. Meanwhile, we need to think about short-term damage control while we're getting this energy system change. Finally, none of this will happen fast. We're talking multi-decades, probably half-century time scale. And that's why I say we need both boldness and humility. We need to be ambitious, but we also need to be realistic. So let's start with the science. And this is not a chart you usually see, and I'll explain it. The top is CO2 emissions. The business as usual is the blue line. You know, here we are in 2011 at about 40, almost 40 gigatons of carbon. You know, this is the trajectory we've been on, and with China and India, continuing economic growth, we're expecting this kind of trajectory. And that leads us on business as usual by the end of the century to about 900 ppm, parts per million of carbon dioxide in the atmosphere. In terms of temperature increase, well, that correlates with about a 4.5 degree temperature increase above pre-industrial levels. So that's part of the story. Now, the other part of the story is the system doesn't respond quickly. Let's say we were to start a 3% reduction in CO2 emissions from the energy system globally beginning in 2025 and drop almost to zero. You would think we'd get a linear response from the atmosphere. I mean, I think that's out in the popular culture. It's kind of like a dial. You just dial back and lo and behold, the atmosphere cleanses itself. The point of this is that, and this is a pretty midstream account of climate sensitivity, the rate at which the atmosphere responds to carbon dioxide loading, you actually get more of a plateau. So even though you're dropping the annual emissions, the inertia in the system is so significant that you really only about stabilize at the level that you're at in terms of concentrations till the end of the century. And then you kind of begin a slow bleed, and about 1,000 years later, most of it is gone, or 3/4 of it's gone. But it's that kind of time scale. What that means, if you're going to hit the 2 degree temperature mark, and that's there's nothing magic about that number, 2 degrees above pre-industrial levels. It happens to be a temperature level that human beings have never seen on the planet, but it's an arbitrary measure of the danger zone for climate warming. The European Union has adopted it as the sort of official line we don't want to cross. What this chart implies is to hit that 2 degree mark, we need to be on that kind of trajectory, which means zero. So, again, anything that you've heard in Congress being debated has nothing to do with zero. It has to do with like 15, 17%, maybe 50, and even 80. I mean, the point is that the discourse just really isn't there. Now, why do I bore you all with this? Because the implications it has for the energy system. The scale, if you take nothing away from this talk except the scale of this problem is unbelievable. It's like nothing else you've ever really thought about. So let's just think about what it would mean to drop global energy CO2 to zero. Here we are in 2010 at 16.5 terawatt equivalent of energy. It's a frequently electricity measure, but that's all energy. On a very modest growth trajectory, by mid-century, we're expected to be about 30, and on an even more aggressive growth trajectory, more like we've actually seen for the last decade, maybe about 39 terawatts. So what this implies is that all of that growth and the base on which it builds has to be zero carbon by, 2025. Okay, we're not going to do this, okay? But I think the point is that if you wanted to do the 2 degree thing, which is what everyone claims they're trying to do, you would need to basically replicate the entire energy infrastructure of the planet, every car, every building, every factory, every power plant, to a zero carbon fuel, if you will, and you're going to have to do it in 35, 50 years, and you're going to have to build the infrastructure, the entire energy infrastructure of the planet, twice or 3 times over, and it all has to be zero carbon. So, and then what are we going to do with the weekend? I mean, that's sort of the point. The point I'm trying to make here is that let me kind of describe it another way. So here's a typical reference scenario for CO2 that you get from, say, the International Energy Agency. Here's where we want to be. Again, it means decarbonizing all electricity generation, shifting all transportation to electricity or zero carbon fuels, shifting all industrial processes to electricity or zero carbon fuels, shift all buildings to electricity for heating, cooling, and ventilation, do this in 40 to 50 years, And as I'll mention later, given time lags and imperfections, we're probably going to have to figure out ways to extract CO2 from the atmosphere. This is a big lift. Now, why do I mention small is not beautiful? This is going to date me. People of a certain age, like me in our 50s, remember these books. We remember them very well. Maybe some of you are even studying them. I don't know. But my generation, really, these were the iconic books in the 70s on this topic. And actually, this is how I got interested in the topic. Amory Lovins' Soft Energy Paths, which was adopted from a famous 1976 Foreign Affairs article. And then, really, its inspiration was E.F. Schumacher, a British economist who wrote Small is Beautiful. And, let me just say, Amory is a friend of mine. Amory's been a house guest of mine. I like Amory. But, the vision that Amory put out there has been extremely influential in these debates. And basically, Amory's vision was, okay, here we are in 1975. What he called the hard path is we're going to continue to use coal. Oil and gas will taper down, and nuclear at that time in 1975, people actually believed that we were going to have about 1,100, maybe 2,000 nuclear plants, and that was what he called the hard path, which was capital intensive, very centralized power generation, and so forth. He contrasted that with what he called the soft path, which was basically energy efficiency would reduce our demand instead of this kind of trajectory. On a global basis, we'd get something more like this. Coal would disappear, oil and gas would disappear, and by 2025, we would all be basically living on wind power, solar power, and biomass. So I just put this out there as a vision. Now, that may, I don't know how you all react to that. It was the gospel when I was in college. This is what we studied, this is what we believed, and I want to tell you why I think it's been misleading. Al Gore repeated the same, kind of the same goal. In 2008, I challenged, to do 100% renewables within 10 years, even. So it's out there. Emotionally, I'm drawn to that. I was in my youth, and but when you look at what really would be necessary here, you really have to do some numbers, and you have to think about this from a standpoint of scale. And I'm going to just show you some numbers we put together and some analysis based on a range of these kinds of studies that, one of them comes out every other week by some environmental group or the IEA or the U.S. government. It's like, how do we get 50% reductions? How do we get 80% reductions? And it's very instructive to go through this sort of analysis to see what kind of assumptions. Let me just say the hopeful view that emerges from these studies is something like the following. This is kind of Amory Lovins 2011. Improvements in energy efficiency can take care of a substantial portion of growing global energy demand. The current generation of renewables, including biofuels, can largely take care of the rest. In fact, World Wildlife Fund just came out with a report this week, I think, that said that. This can all be done by 2050 with current technology, no big innovation needed. This all can be done by 2050 at modest cost. In fact, some of these studies will claim we'll save a lot of money. And aggressive emission reductions in the U.S. and EU will actually, matter. So that's the high church view. So I'm going to do a little deconstruction here using some very simple numerical illustrations. The first point is that to achieve the energy intensity or the energy emission reductions to go from this to this, which is kind of what the green scenarios, a lot of the green scenarios would project, you really have to do the math and say, what is the energy intensity that would have to be a reduction that would have to be achieved? That is, how much every year would we have to improve the amount of energy input per unit GDP? And you can see, you probably can't read this, but the studies kind of cluster around somewhere around 3.5%, 4% per annum reductions. What's instructive is that actually what the OECD achieved over the last decade and a half has been closer to like 1.5%. So we're talking about tripling the rate of energy efficiency improvement, essentially. Can we do that? Maybe. Let's look at that a little more closely. I would have more confidence that we could do that, or even get close to it, if we were talking about the U.S. and the EU. But the reality is that most of the energy growth projected energy growth on the planet over, say, to 2035 is non-European. It's China, India, and the other ASEAN countries. That's that big ball. 90% of the projected growth is from non-OECD, and 52% of the growth is from China and India alone. You've got Latin America, Eastern Europe, and you can see US very small, EU very small. We have stagnant demand, essentially, in this country, for all intents and purposes, certainly compared to this. So what does that mean? What does that imply for energy efficiency and reduction in energy demand? This is the central fact that is often not acknowledged. The developing world has a lot of what I'll call latent suppressed demand. That is to say, here we are, this is energy intensity, this is the amount of energy we consume per capita. Here's North America, Russia, OECD, down to China. This is where China was in 2003, but even in the last 7, 8 years, they've already come up to here. Other Asia, Africa, India. So my point, 2 billion people on the planet don't have electricity right now. This is a lot of growth that's going to happen. This is not extravagant growth. This is like people's first light bulbs. This is people's in large apartment complexes. It's air conditioning. It's heating, cooling, and ventilation. So my thesis is that you've got so much area under this curve of the developing world just getting to not even OECD standards, let's say Bulgarian standards or South American standards. There is so much volume in here that even if we were to chop North American demand in half, you're not going to really make a dent in this underlying demand. So I think when you hear these kinds of claims, you really need to look at the math and say, where is the growth coming from? How much of that's going to be displaced by energy efficiency? If we look at California, another myth I want to explode here is that we've actually made significant absolute reductions in the United States in energy demand through energy efficiency. This is a study from the California Energy Commission, commissioned from the Stanford Precourt Center, and the study said, well, here's 1990 electricity demand in California. If we had no energy efficiency policy, we would have been here because of population growth and GDP growth, and through a variety of programs, we suppressed demand by 10% over really 25 years, basically, of policy. Now, that's not nothing. 10% is a lot, but it's not 30 or 40% or the kinds of numbers you see in these studies. And California is the paradigm case of a developed world, energy efficiency regime. So I'm not belittling California's accomplishments. I'm just saying that you'd have to triple it or quadruple it to come up with the kinds of numbers that you get in these various studies. Looking at another way, let's say this is let's take a modest view of energy demand growth. This is business as usual. What if by 2035 the entire world was consuming per capita the same as the average Chinese person consumes today? Yeah, you'd get some reduction, but you wouldn't be on a decline. You'd be flattening. And as I said, that's a substantial contribution, but it's not bending the curve. If the entire planet were living on California's energy requirements at its high efficiency, you would get a number more like that. So I guess one of the themes here is there's no silver bullet. That's a great cliche, but it's I think it's good. None of these solutions, I'm going to argue the soft solutions have some particular vulnerabilities. None of these solutions are going to deal with the CO2 problem by themselves. So let's now look at this. That was the demand side. Now let's look at the supply side. And I know this is going to be familiar to lots of you, and it's going to seem like an oversimplification. So let's we can get into this in the back and forth. But let me give you the sort of high-level view on what's wrong with relying on the soft supply side, as so many of these studies do. The first point is that renewable energy, unlike coal or nuclear, the sad fact is that it doesn't supply steady 24/7 power. That's a big deal because a lot of the world's energy demand, particularly in the electricity sector, is 24/7. We're talking about, large cities. We're talking about transportation systems. Sure, we have some fluctuation, but the amount of embedded base energy is very large. This is the German performance, the output of German wind farms. This is one particular wind farm. This is a group of wind farms, and then finally the green line is an aggregated group of wind farms over a period of months. And you can see a lot of variation and even within days, a lot of variation. If we exploded one of those days, you would see pretty substantial fluctuations over the period. Now, why is this significant? Why am I mentioning this? Because we don't have the ability to store that energy, there's some very significant physical and economic limitations to the degree to which wind power, as an example, I'll talk about solar in a second, is going to displace high carbon power. First of all, you got to do something to fill in those valleys when the wind isn't blowing. And in most of the country, that's a gas turbine, which is going to fill in or is going to dispatch to fill in the hole. That has pretty significant cost, and gas is not carbon-free. A recent study by the California Energy Commission concluded, in fact, that as California went to very significantly high levels of wind penetration and solar, as compared with, say, idealizing another path, which would be nuclear or carbon capture and storage, it was actually the renewables path that had the highest CO2 emissions. That seems completely counterintuitive, but it's because of the amount of gas you have to dispatch to follow in behind the wind. Now, if we had energy storage, and we could just, when the wind blows at night, we could store that energy and run it during the day, and that was economic and so forth, then we'd be good. But the fact of the matter is that doesn't exist in an economic form right now. And actually, that's my point, is we need to work on that. Other ways to deal with this are very wide area network cooperation, or just build a 2,000-mile transmission line so that when the wind isn't blowing in Texas, you've got it in North Dakota. That's another big infrastructure investment. Also, better forecasting so that you're timing better and you're understanding better what dispatches at what time. The point is, this is all complicated. It adds costs, and in some cases, like Texas, so let me just move forward here for a second. There's just some times when the wind doesn't blow at all. This is the Texas grid on August 1st of this year, and a lot of August looked like this. Here's the demand on the Texas electric grid. The blue line is the installed wind capacity in Texas. The red is what wind was actually dispatched. Now, you'll notice two things. First, the wind contribution was pretty small compared to its installed capacity, and I'll get to that in a minute. But also what's interesting is at times of peak demand, the middle of the day, the wind was making the least contribution. So all those valleys have to be filled in by in Texas natural gas, because that's going to be your marginal unit, or your marginal. So this raises another point, that renewables have low capacity factors. Unlike a nuclear plant, which typically will run 90+% hours of the day and year, or even a coal plant or a natural gas plant, which can run at very high levels. Wind capacity factors historically have been much more in the range of something like 30%, 35% maybe in the U.S. Now, in some places it's more, some places it's less. But I'm sorry, that's the popularly cited number. The reality is that the actual monitored levels have been closer to like 20, 25. So these studies are making very optimistic assumptions even about these low capacity factors. Similarly, solar is typically, in the U.S., maybe 15. In places like Germany, you're really talking about 10%. It's a very cloudy place. And why the Germans just spent $100 billion on PV is beyond me, given how little power they're actually getting out of it. It's very expensive stuff. So what are the consequences of this capacity factor issue? What it means is to achieve the same emissions displacement, even assuming a level output. Put aside the intermittency issue, just even assuming a steady dispatch, each gigawatt of baseload must be replaced by 3 to 10 gigawatts, must be, or backed up, I should say, that's probably the wrong word, not replaced, but backed up by 3 to 10 gigawatts of wind or solar, because you have to compensate. That's just the math. That's cost. It's also much greater impact on land area. Transmission also has to be built, because you've got these large swings, and if you've got a wind farm located at the end of a line, you have to build the line so that when the wind is dispatching, it is able to be conveyed through the line, but a lot of the times the line could be empty. Just a couple of very concrete examples of this kind of effect. This is a power plant in Florida. There's a thermal power plant, there's a coal plant, and a combined cycle gas plant. Just to take an illustration, all these solar thermal concentrators here produce as much power as this combined cycle gas plant, as 1% of this of the output of this plant. So you need 100 of these to equal one of those. Another example from my neck of the woods, this is the Cape Wind project off of Cape Cod, which is a 25 square mile swath of ocean dedicated to wind power. There's an artist's visualization of it. A lot of people, including Robert F. Kennedy, don't like it. Same amount of power output as this combined cycle gas plant. So, there are trade-offs here. This low power density problem is a real problem for renewables. A way of looking at this mathematically, I stole this from Václav Smil and some others. Another way of thinking, this is a log scale, and power density, the concept is watts per square meter of land. And as you can see, coal, nuclear, whatever else you want to say about them, they have relatively high power density. You get a lot of power out of a limited land area. Similarly with natural gas, and even if you take into account the natural gas field. But photovoltaics, wind, biomass are here. They're orders of magnitude difference in terms of amount of power you get out of land. Now that's not a theoretical concern. A lot of conflict in the United States about building these things, and believe me, I live maybe not so bad in Texas, but I know you're citing a lot of wind, and you got a lot of places where farmers are happy to accept it. But a lot of the world, that's not the case. There's some pretty fierce battles. A final point I want to make about low power density, dispersed, soft energy is that you have to build a lot to get the same effect, and you have to build a lot of units. I mean, when you're talking about wind plants versus coal or nuclear plants, you're talking about millions of wind plants versus, let's say, hundreds of coal or nuclear plants. This chart just takes some of these studies that I put up earlier and looks at the deployment rates on an annual basis that are required in the studies versus actual experience, which are the red lines. And you can see what these studies are calling for are build rates that are many, many times the rate of historic experience. Now that's even before we get to cost. All right, assuming that cost weren't an object, which it surely is, and we can get to that in a minute. That's the politics part. But this is pretty much your market proxy right now for, let's say, electricity. Combined cycle gas plant, let's push it up even to, let's say it's a 6 cent, to build and operate a combined cycle gas plant. Most of your renewables are way north of there, and I would argue this is even conservative because, for example, the cost of backup power and transmission is typically not included in these estimates. Biofuels we could have a whole session on. Let me just say that the notion that biofuels are some kind of panacea here is, when you hear that, you need to really closely examine those claims. The biggest flaw with the notion of biofuels as a major contribution to global decarbonization is the fact that you got to grow the stuff, and at the volumes you have to grow it, it means displacing a lot of native forest, which we're seeing right now. We're seeing forest in Brazil, in Indonesia, and other places being ripped up for biofuel soy plantations and the like. And that means not just local environmental effects, it also means very substantial impacts on climate, because when we remove a carbon sink, i.e. a forest, and replace it with a crop, we're losing very substantial amounts of net carbon. Not to mention when you burn the stuff to begin with, when you burn the forest to begin with to clear it, you're releasing a lot of CO2. So the science is really just beginning to look at this, but again, it's an example of how good intentions, soft energy, this was a central plank of Amory Lovins' vision, from which, to my knowledge, he hasn't really backed off. Now the claim is, well, second-generation biofuels will take care of this. We'll be using the cellulose, we'll be using the lignin in the plants, and not the leaves, and we'll be fine, and everything will work out. And we'll see. Still, you need a lot of land to do that kind of stuff. Maybe breakthroughs in genetic engineering will get us past that, but we're not there at the moment. I want to address gas quickly because we're in the middle of a gas boom. You may have noticed that down here in Texas and in Pennsylvania, Appalachia, North Dakota, and now probably in Ohio. Again, gas displacing coal could help, but to get to that kind of zero number, that 80% number, it's not going to be a complete answer. This is just a quick set of numbers. This is just arithmetic. If this is business as usual, if you replaced all the coal plants in the United States with natural gas, you'd get this kind of trajectory, which is, again, like energy efficiency. It's a contribution, but it's not the drop you need. So, you know, that's the case against over-reliance on soft energy. I'm going to make an argument that if we're going to do innovation, we need a lot of innovation both in soft energy and hard energy. But I would nominate the three central priorities based on scalability as, first of all, we need storage and other kinds of options to deal with renewable energies and to make that a much more functional part of the grid. And we can talk about some of those options in a minute. Transforming fossil energy, let's face it, folks, we're going to use gas and coal in large amounts for many, many decades. So the question is, how are you going to decarbonize it? And the carbon capture and storage is something that's been practiced at small scale, and we're beginning to scale it up, but we need to move a lot faster. And finally, maybe the greatest heresy of all for the green movement is we have to be starting, if we're at nuclear power 2.0 right now, we need to be looking at 3 and 4, probably starting with small modular nuclear light water reactors and then moving towards more advanced concepts. Let's start with energy storage. This is an example of a compressed air energy storage system to deal with variable generation. Typically, in fact, one of these is being built as we speak in West Texas, a pilot scale plant that basically takes the energy from the wind power when it's blowing, you know, predominantly at night or in the early morning, puts it in a salt cavern, or uses the electricity to run a compressor, which compresses air into a salt cavern. When the energy is so here during this time at peak times, your peak production, you're storing this power, and then when demand rises, you release it and run it through an expander turbine to produce electricity. So at a reasonable site, you may need 2 to 3 times the installed capacity of wind compared to the power you're providing, but it does provide steady power. So there's still the overbuilding problem, but at least you don't have the intermittency problem. This is something that needs a lot of work, and almost nothing's been spent on it. A lot of money's been spent on batteries, but that doesn't necessarily appear to be the most advantageous approach. Again, coal or gas with carbon capture and storage. We could do 3 days, a seminar in this. I just wanted to put the visual up there so that you have it in your mind, and you know, I know some of you are probably looking at this more closely. Suffice it to say that no one really disputes you can do this. It's been done. It's been done predominantly in the context of extraction of CO2 for enhanced oil recovery. When you inject CO2 into a depleted oil deposit or nearly depleted oil deposit, you increase the rate at which you can extract oil, which has been a positive from the standpoint of getting carbon out of the atmosphere, at least initially from the sources. Ultimately, you're getting oil out, and if you continue to run transportation on oil, you have CO2 emissions. The point, though, is that extracting coal, CO2 from a coal power plant and injecting it into what's being discussed mainly now as deep saline aquifers is something that's being done at pilot scale around the world, almost commercial scale, like million-ton a year. Typical coal plant will put out 3 or 4 million tons of CO2 a year. We've got million-ton a year pilots running right now. All kinds of questions about will it stay down. The Intergovernmental Panel on Climate Change panel on this says 99% chance that it'll be down there 1,000 years. It's all about site specifics and doing it right. We got a lot to learn. My contention is that if we don't do this, you pretty much give up the game, because you're not going to do the rest of it in 50 years or even 100 years with the renewable sources or with efficiency. Underground coal gasification is a variation on this. It's actually an interesting technology because, A, it's really well known, and the Soviets did this. Australians, the Chinese are doing this now at commercial scale. Basically, instead of mining the coal and burning it, you're injecting oxygen, air, and water into a coal seam. The chemical reaction gives you a synthetic gas, which is hydrogen, methane, CO2. A lot of the really nasty stuff stays underground. You clean up the gas, you run it through a gas turbine. And what's interesting is because it's coming up under high pressure, you can use that pressure to re-inject the CO2 into a formation. The attractive part of this is that it's really cheap because you're avoiding the costs associated with mining and transportation of coal. Small modular nuclear I mentioned as kind of let's call it Gen 3 or Gen 3 plus. This is just an example of one commercial product that's being offered by a company called NuScale. This is like a typical large nuclear plant would be about 1,000 megawatts. These are like 45 megawatt modules. You can put them on flatbed trucks. You can bring them to site. You can build them as modules as demand grows. One of the things that sunk nuclear power in the 70s was trying to take on a capital project, a multi-billion-dollar capital project, all at once, and having to finance that and have all your eggs in that basket and be betting on demand. This technology, I won't go into the safety features. Some of these would be actually underground, so you don't have the issue of radiation on the surface, and some of them are designed to be underground. The water, the coolant to core ratios are higher, all kinds of other things. I'm just putting it up there to let you know it's out there. It's being discussed as one way to practically take on this the nuclear part of this. Advanced nuclear, there are a lot of ideas out there. I'll just pause on one, which is liquid salt thorium reactors. The United States actually messed around with this in the mid-'60s till we decided that we didn't really want to do this. We wanted to stick with the light water version, in part because the light water reactor gave us more bomb-grade material. So, actually, the very advantage of this, which is a much more nuclear proliferation-proof or safe system, was actually something the military didn't want to see. They wanted plutonium. But anyway, people are now talking about reviving this technology, and actually, part of the story is the Chinese and the Indians are ahead of us. The Chinese are saying they're going to build something like 20 gigawatts of this stuff by 2020. And the Indians have a commercialization program. The U.S. is nowhere on this. Just interestingly, I showed you those deployment curves earlier. I'm not necessarily going to make a pro-nuclear pitch as such, but I do want to point out that in terms of those study deployment rates assumed for nuclear, you can see that actual historical experience, at least for a decade or so, was in the 30 gigawatt a year range, which kind of aligns with some of these studies. So I would argue among all the things that are being discussed, nuclear is the one place where we've shown when we want to do it, we can do it fast and we can do it at scale. I want to switch a little bit and talk about why globalization might help us rather than hurt us. And actually my organization, you can go online and look at our China program. The reason we have a Beijing office is because we think China is really critical to getting advanced renewables, advanced coal, advanced nuclear going, advanced storage. The fact of the matter is there aren't any energy markets in the U.S. right now, or at least they're not electricity markets of any consequence. Our demand has been decreasing for quite some time, several years. We're maybe beginning to see a little uptick, but we're not going to see the sort of 3, 4, 5% growth, much less the 10% annual growth that we're seeing in China. China and India are real markets for new energy, unlike the Europe and the U.S. And the nice thing about a growing market is you can add a little incremental cost to build clean. In the U.S., if I want to build a clean plant of any kind, I have to compete against the marginal cost of running a coal plant, which are like 2 cents, 3 cents. And I've got even a gas plant will have a hard time competing with that, much less a 7-cent or 12-cent wind plant. So that's the first point. China's liquid. It's got money. We don't. China, fast construction times. I'll show you an example of that in a minute. Lower cost construction. And also, this is a larger topic, but we often think, the Chinese and the Indians are just copying Western technology. In the areas I'm familiar with, they're actually creating a lot of stuff that's called reverse innovation, which is kind of an unfair term. It implies only we do innovation and they do reverse innovation. But the reality is China and India have a lot of talented engineers. They're making a lot of original technology contributions. And so it's actually important to be on the ground for that. This is an example, a post-combustion capture unit outside of Shanghai, Huanan Power. This is a capturing carbon, an example of what I mentioned earlier. This plant was essentially built in 4 months. Now, in the United States, you're really talking multiples of years probably to build something like this. I want to kind of conclude by talking about damage control, because the steepness of that lift, the decarbonization lift I showed you, is, I mean, you could definitely walk out of here and, just want to end it all, right? Like, how are we possibly going to do this 2 to 3 degree thing when we've got this sort of that much stuff to do in the next 50 years? So that's why it's really important to be looking at damage control, because we're going to likely breach a 2 or 3 degree threshold if we rely on energy system transformation for CO2 reduction alone. The problem with that is that you may not be able to go backwards on some of these critical climate thresholds. Now, we don't know exactly that that's the case, but there's some pretty good evidence that we will. This is a recent paper by Molina, et cetera, and this is kind of a probability of distribution. The basic argument is we're already at 2 degrees. We're most likely already here, and the only reason we haven't realized 2 degrees yet is all the sulfur we've put in the atmosphere from coal plants, and we're now removing that sulfur. Sulfur masks warming. It cools the planet. Now that Chinese are finally scrubbing their coal plants, we're getting warming. So, kind of a little perverse part of the environmental thing. So in any way, but if you look at what people think might be in a range of things that we would see happening in that sort of 2 to 4 degree range, it's not pretty. As an example, this is the Arctic sea ice extent we've been seeing in the summer, and as you can see, 2011, was pretty low here, 2007, but you see a steady downward trend in the amount of Arctic sea ice. Can we recover if we end up with an ice-free Arctic in the summer? Can we regenerate ice later? Maybe. Do you want to risk that? Maybe not. So let's talk about the category of damage control options. One is to deal with the short-term warming gases. I showed you that curve that shows that CO2 lasts essentially forever in the atmosphere. As far as we're concerned, a couple centuries is forever. But methane and black carbon, which are also warming gases or emissions, decay pretty quickly, like a decade or even weeks, once you cease to emit them. So we might want to look at that. Accelerated carbon removal from the atmosphere through biological and chemical means, that is, sucking it out. And then what I'll call geoengineering, which sometimes overlaps with this, including what's called solar radiation management. This chart just shows you that actually CO2 isn't the only warming agent on the planet. Methane, ozone, black carbon, also are actually equal right now. Now, in the long run, this is what matters. In the short run, this is providing a lot of warming. So if we can deal with methane, for example, through capture of methane from coal mines or anaerobic manure digestion or sewage treatment, or being better about how we extract oil and gas so we don't get more methane leakage, we can probably make a dent. Air capture of carbon seems like a science fiction-y idea, but it's being tried at scale. Literally, you're talking about sucking air out of the atmosphere and running it through a chemical process that separates the carbon and then injects it underground. So instead of pulling it out of the flue gas of a coal plant, you're pulling it out of the ambient air. Aggressive afforestation. This is the kind of discussion you're beginning to see. Should we look at places like the Sahara, the Australian outback, to really, step it up in terms of terrestrial sequestration? I know a lot of this stuff sounds totally bonkers, but when you're looking at the kinds of numbers that I'm showing you, I'm telling you, you got to be open-minded about this stuff. Solar radiation management concepts range all the way from, I'm on the board of directors of an organization that's looking at, the potential testing floating white surfaces in the Arctic, biodegradable white surfaces. You can laugh at it, but say actually the calculations suggest you get a lot of reflection of energy back into space through this sort of stuff. People have talked about putting drone ships out into the higher latitudes and injecting, basically putting saltwater spray into the air, which is light in color and puts energy back into space. If you want to go deeper on this, there's a recent report by the Bipartisan Policy Center which looks at all the options, and basically where we're at on this is research. I mean, no one's talking about deploying this stuff at any kind of scale, but people are talking about looking at the research. Couple final points. None of this is going to happen fast. Energy transitions are slow. Even things like coal take, decades, centuries to penetrate markets significantly. So, think 50 years. And then finally, so my takeaways again are, I think to deal with this problem, you have to be both aggressive and realistic. Think scalable. Small, soft is not always beautiful. The third is we just don't have a complete solution set. Anyone who tells you we have all the technology we need, all we need is the political will, look at those claims very carefully. China and India as innovation test beds and engines are important to think about. And then finally, be humble, because our predictive capacity in energy has proven very weak. I don't think anyone in this room would have thought that shale gas had tight gas would be producing, it was estimated to produce something like 30% of U.S. gas demand by 2025, which is now kind of the mainstream estimate. I mean, things come out of nowhere. Back in 1975, we thought it was all going to be nuke powering the grid, and that turned out differently. So with that, I'll stop and take questions. Or comments.
Questions?
Yeah.
I'm not a climatologist or something, so but if all of the deployments, based on what we just estimate that everything that you wish comes true with regards to U.S. and EU taking steps to actually do all of these things, and there is zero, reduction of emissions. I did a research, with a couple of folks, and we looked at some of the UNFCCC data over the summer, and we sort of looked at, what kind of mitigation, and our research was pretty much inconclusive because U.S. is emitting and EU is emitting, but we are talking about Africa and South America at the same time. Then we begin to look at, deployment, intellectual property rights. How can you deploy a lot of these things from the U.S. to a lot of these countries? And, it's so big. So even if there is, zero reduction in emission in the U.S. and EU and all of this, how does it play any significant role in actual global, reducing? I
mean, it's a great point. I thought, you're just making a point I didn't make very well, which is that even if the EU and the U.S. got its act together in Japan, we're still going to be something like, by 2050, we're going to be something like 25% of the CO2 problem. I had a slide that I took out that shows that. So, yeah, I mean, if the developing world doesn't do this, nothing that we do is going to matter. Except that, and here's the argument for the U.S. and the EU leading, is that there has been a historic pattern of technology diffusion in which the West has, developed major technologies. And, if you look at Africa or you look at Latin America, basically running on European and U.S. car platforms and so forth. So I think the argument would be, the political argument is we got to lead or else they'll never do it. Although now that's being inverted since China is moving faster than we are. So, but the other point really is one of there is still technological capability. So the argument would be the U.S. and the EU, I would make this argument, we have an obligation to at least do the research and innovation work, build the first 5 units of something, get the costs down, get the and maybe cooperate with China on that. And we spend our money, and then that technology is going to diffuse globally, we hope. That's really the argument. But if it doesn't diffuse, we're basically, we'll manage some reductions, but zero reductions globally is, it's really not going to happen. I mean, let's face it, it's not going to happen in 50 years. And that's why, honestly, people are looking at the geoengineering stuff, because they're saying if we get to the point where we've got the kinds of weird weather 20 years from now, just imagine the kind of droughts that you had in Texas, but every single year and worse, people might start talking about putting drone ships in the Arctic and shooting up sea spray. I mean, actually, you pencil that stuff out, it's not very expensive. I mean, we're talking a few $1 billion a year versus that program. The zero program is trillions, not a year, but probably several trillion over a couple decades. So I guess my point today was to get you to think about this exact point. This scale is almost ridiculous to think about, and yet we have to think about it. Because if we don't, and we just piddle around with our green energy, flavor of the day, it's not really going to do very much.
So you said at the end that a lot of people say we have the technology, we just don't have the political will. What I hear more often is that we have the technology, we don't have the money. What's your take on, say, carbon finance and the role of economic incentives for making some of this stuff happen?
Yeah, I mean, that's in theory, I'm really attracted to the cap and trade stuff, and we supported it, and all of that. Yeah, it would add something, but the kinds of numbers that are politically doable for a broad carbon price right now, the U.S. was talking about maybe a $20 price or maybe a $7 price by 2020. The incremental costs of some of these technologies is significant. Here's my argument for an innovation policy versus a broad pricing policy. Well, maybe not versus, but certainly in addition to. With an innovation policy, if you took, say, $20 billion a year, which I think is a doable number for the United States, we spend $80 billion on R&D for the Pentagon. If you took $20 billion, did it on advanced energy, you would be able to build enough stuff to manage the costs down. And it's actually maybe a lot cheaper, and you would get more innovative stuff than if you just throw an incentive out there. Let me give you an example. The current renewable portfolio standard, or the investment tax credit for wind power in the United States, basically you produce wind, you get a 2-cent tax credit per kilowatt hour. But it's not incenting anyone to do innovation. It's basically incenting you to take something off the shelf and build it. So I would say we're already spending $6 or $7 billion a year in taxpayer expenditure for wind power. I would say if you could reprogram that money, if you had to, if it was a zero sum, I would reprogram it towards let's do wind with storage, or let's do carbon capture, or something else, and multiply that. So I think there's a broad versus deep, or there's a focus problem here we have. I think the theory of cap and trade or carbon tax is nice, and it certainly wouldn't hurt. But I'm not sure that at the kinds of levels that people are really thinking about now, it's going to get people to invest in the truly innovative technology. But, that's an arguable point. Yeah?
So I couldn't tell from the chart, but was that a pebble bed reactor or yet another design, and whatever happened to pebble bed?
Well, that's interesting. The U.S. kind of dropped it. South Africa was in the lead. For those of you who don't know what a pebble bed reactor is, it's instead of a big fuel rod, what you have is a bunch of little pellets of uranium that are encased in this glassine, kind of thing. So the chance of a runaway reaction is much diminished. The U.S. kind of gave up on this. The South Africans are in the lead. They gave up on it. Now the Chinese, Tsinghua University is sort of the world's leading pebble bed research center on, there may be some other things going on that I'm not aware of, but I know that at least China is pretty serious about this. But we do not have a program in the U.S. on this right now. Yeah.
Yeah, so kind of a lot of your talk, you really just sort of bring up the scale, of the whole issue, and it really just seems like, green technology, renewable energy just isn't, up to the task. So given that, we've been influencing the global climate for, 100 years significantly with not only CO2, but sulfur, nitrous oxide emissions, things like that, at what point do we really just need to accept that we really just need to grab the bull by the horns and just learn how to manage the system rather than try to just bring it back to something that we liked before?
So you're making the argument for geoengineering, which
I think it's inevitable. Or what do you think?
Yeah, well, it's not something I'd like to admit, but I think that there's a scenario in which that happens. Now, the caveat on all of this is those numbers I showed you. Look, climate science is pretty certain the direction we're going. There's a lot of debate still about how fast. And how much, what's the real climate sensitivity? Those debates will continue. So in the best case, we have 100 years before things really go out of control, in which case we might decarbonize a lot of the energy systems in 100 years. A lot can happen in 100 years. But I kind of leaning to the view that, we're already hacking the planet. Basically that's what we were doing with CO2. And a lot of people will argue from a moral standpoint, we have no right to go in and intervene in the climate system by putting sulfate or by putting sea spray in the air or by putting white surfaces in the Arctic, that's an immoral intervention into nature. And I think the counter-argument is, hey, buddy, we're already there. We're already doing it. So what we're doing is trying to hack in the other direction. Now, I will say there's going to be a lot of scientific debate about whether some of those interventions have unintended consequences. And I can show, modelers will say, I went to a conference last year where the sulfate or the sea spray in the Arctic thing was countered, and they said, well, that means drought in Patagonia, because of the global circulation. So there's some caveats on that. But my own view is if things really continue to deteriorate, I think countries are going to start to do it unilaterally anyway, to protect their own interests. And then you're beyond research. I think we have a window now to actually do the research. One nice thing about talking about it is that it makes people more interested in decarbonization, because it's a pretty scary thought. And you know, the thought that we're actually going to have a global governance mechanism to control geoengineering, I mean, come on. We really can't control nuclear weapons proliferation. You know, are we really going to be able to do that? So anyway, so I hear you, and I'm almost there. Yeah. Any other questions, comments? Yeah.
Yeah. So I think if I understand right, your central premise is we need an all of the above strategy, right? Yeah. It's not that the soft things can't contribute renewable energy, you know, whatever.
Soft is not always beautiful.
Yeah, it's not always beautiful. It's not that.
Right.
But I do want to push back a little bit on the renewable energy stuff. You know, here in Texas, obviously the wind energy has done very well. We've generated as much wind energy in the last year as we have nuclear power, and there hasn't been an increase in the need for backing power. There hasn't been an increase in the need for ancillary services in Texas correlated to that. Now, if we get beyond that 8% number, there probably will be a need. But there's obviously a lot of room to go for a lot of other states before we get to that point. And Texas is obviously the smallest grid, so for other grids there might be even more room to go. So, you know, it seems like it goes back to your central point, which is that we need an all of the above strategy, but we also need to acknowledge that there's a lot of room to grow in those areas.
There is. I accept your statement. I want to offer a friendly amendment, which someone else in the room can probably defend, but he's not here, is that the wind system in Texas is using ancillary services and it is using backup generation. It's just it hasn't necessarily occasioned the need for new construction of facilities. So it's not quite accurate to say that the wind is not drawing on significant fossil energy from the system.
I guess what my point then was to refine it is that the change, there has been no change in the use of backing up systems in terms of total megawatt hours used. The ancillary services systems in ERCOT over the last 10 years, you know, that correlates with the growth in wind.
Okay, that's interesting.
But I'm fully recognizing that once we get past the point we're at now, that's probably going to change.
You're like at 15% now.
Well, we're at 8% generation.
Generation. So. Okay, that's a fair point, and I think that's there are limits to all these systems. You know, 20% is the folklore. On the other hand, Denmark's running at 25%, and you know they don't seem, but they've got all kinds of interconnections to the continental grid. But it's a good point. I don't want you to take away that soft energy has no contribution here. I think it actually could. I think we're going to need a lot of innovation even in that space. So, Varun, do you want to keep going here?
Two more questions.
Yeah. Okay.
One question here and
Yeah.
All right. You had.
Yeah, that's fine. That's fine.
Okay.
Yeah.
You had mentioned that there's limitations of using terrestrial vegetation to scrub carbon dioxide out of the atmosphere, using it as absorption or infrafuels. What about using marine vegetation?
Right.
I mean, there's a much more surface area of the ocean. And
right. That's actually a geoengineering concept that's been put out there, iron fertilization of the ocean. That's a really controversial topic with biologists, but it's out there. It's out there, and there's no question that the biota of the ocean offers a very substantial amount. The reality is right now the ocean is taking up a lot of carbon, something like, I want to say, 20% of the carbon on an annual basis right now, and oceans and forests together maybe as much as 50%, but on temporary basis. But the people are talking about how to accelerate that with tampering. And all I can tell you is the biologists go totally bonkers when people talk about increasing biota in the oceans. But just to let you know it's out there. Yeah.
Considering that liquid salt nuclear generation has virtually no chance of catastrophic meltdown and that it shuts down by itself, how feasible do you think it is for the U.S. to implement policy to drive nuclear innovation in that direction?
My organization is pushing a nuclear research agenda that has that sort of thing in it. I think that this is quite promising. I think there is a long history with Americans and nuclear power, and frankly, my generation, reacting in certain ways to it. that I think we may all have to die before this is done. I'm not being, that my generation has to die. You guys are fine. But I do notice a big generational difference in opinion. My daughter is a sophomore in college right now, and we talk about nuclear. She's not particularly bugged about it. She didn't see the China syndrome. She didn't live through Chernobyl. So which of course is that's not even 1.0. That's like negative 0.5. In terms of the development. So I think it's a social perception problem. And look, we could talk all day about nuclear risks versus what fossil is doing to the planet, unabated fossil, but I think the thorium story is a very good one that hasn't been told. And this is basically not much a fraction of the material, much less on the waste end, much more tractable on the waste end, almost proliferation proof, and in terms of the safety features, this complete safety, passive safety. The reaction is not essentially not self-sustaining. So that's in a disadvantage, but it's going to take a heck of a PR job to even move the research forward. Dianne Feinstein has put her foot down and said, as long as I'm chair of the Environment and Public Works Committee, we're not going to have this kind of program. So. Okay. Thank you very much. Thank you.